t equals 1.8 minutes, that's when the 15% blood loss occurred. So that's when it spiked almost instantly to around 35, 37. And then it increases linearly to a certain maximum level. Then what happens is that you have an exponential decay, as I described earlier. You will also notice, so for oxygen, at t equals 1.8 minutes, the oxygen levels just spike up because your lungs are breathing faster and faster. But however, even though your lungs are breathing faster, the blood loss is too great, and in the end, you will lose oxygen over time. And same concept applies for carbon dioxide. And then this is just remaining blood volume, which is just the decay. And then red blood cells are just a proportion of total blood volume, and will follow a similar decay. Now that we've gone through the dynamic case, you may be curious about your own numbers. Say, Dr. Sadovak, if hypothetically this presentation did not receive an A, how quickly would someone die if they were shot 4 times? How would they die? Would they die of oxygen deprivation or by blood loss? Can epinephrine even be optimized to save them? Now I will demonstrate our code in live and show you these possible answers. And obviously, I'm not at that point yet. Now for strengths and weaknesses of our model. So actually, in the report, this is like lacking, but I came up with some stuff. Nice. Unless you guys updated since I looked at it.
No, we didn't.
Sorry. Okay, now it is time to go through the strengths and weaknesses of our model. Our greatest strength is our sheer flexibility. We are able to input any small number of gunshots we want, and we can choose what time we want to insert the epinephrine shot. And with this, we are able to optimize the epinephrine the time of epinephrine inserted for any given gunshot. So it's a very flexible code. And it's also very useful for visualization. So like all those graphs I showed you earlier, the code outputs that, and you're able to visually see how each constituent is changing over time, which is very useful. For some weaknesses, some of our assumptions are very oversimplified, and I would like to discuss some of those. So one of the big ones is that concentration is constant throughout the body for each of the constituents. So that's essentially saying that each artery has the same concentration of oxygen, which is physiologically imprecise. It's probably not true. It's definitely not true. And another weakness is organ functionality. So in the beginning, earlier I said that organs have the same functionality even when shot. But obviously in real life, if you're shot, your heart will start to beat weaker and weaker and not be consistent. Another assumption was that, Another assumption under this category was that we assumed that the lungs and the heart did not consume or generate any carbon dioxide or oxygen. We did that just to make our calculations easier, but in reality, that's just not true. And our last weakness is that we assumed global blood loss, but that is not correct because that's saying that if you're shot in your arm, that is the equivalent of being shot in your liver, which is also not true and is an oversimplification. We need to find some double checking things, like find some experiments and just like compare something with.
Are you sure?
What?
Did they say that? Or?
We should have to compare it to like something that's real.
Is that like a thing we need in a presentation?
I don't think
Actually, maybe we don't need the presentation. That's fine.
Yeah. If we find something that's really good, then maybe you can.
Like we definitely need a report. But so it's all great and well that we are able to write a model and like have code that debugs. That's wonderful. But it means nothing if we have nothing to compare it with, and to see how accurate our model and our code is. So we found some numbers and we concluded that it is accurate.
Let's get 10 size numbers.
We found some numbers.
Let's use 10 size numbers. Let's measure some values for you, and then actually.
In conclusion, I'd say our model and code accomplished our initial objectives. It visualized how blood flows in different organs, and it graphed the accumulation of varying constituents over time. By double checking our results, we verified the model's correctness. Before we part, remember that if someone, or even yourself, is shot, that you should carry a stopwatch with you, set time t=0 at the moment you're shot,
Love it.
and then
T equals 1.8.
and set time at t=0 when you're shot, and run our model. Hopefully we'll have an app for this. Run our model if you want to optimize your chances of survival. Thank you for listening, and I will take any questions.
You can now download Shoot Me on the App Store.
I have a question.
Get shot.
What do you mean by O2